Okay, so welcome back everybody to these short presentations. So the first talk today will be given by Nicolás Vilches on stability conditions on surfaces and contractions of curves. Please go ahead.
Thank you so much for the introduction, and thank you everyone for being here. It's always a pleasure to talk about what I do for my research. So the study that I want to tell you today has to do with stability conditions. And just to give you a brief recap, this is some data consisting of a heart of a bounded T structure and the derived category of a variety, plus something that we call a central charge. The really classical example that you should have in mind is for curves, in which case one can take the as the heart the coherent shapes on the curve, and the central charge involves the degree and the rank. So you should think of some sort of analog of slope stability for curves. There are some properties that I'm omitting here, of course, most importantly, the fact that every object admits a filtration by semi-stable pieces. Uh, in general, constructing stability conditions is actually very difficult. It turns out that the set of stability conditions, it's a manifold proven by Bridgeland in his original paper, but for higher dimension and say, let's say 3 and beyond, we don't know for every threefold or fourfold or whatever that they admit a stability condition. For curves and surfaces, for curves, the construction that I show here mostly works. And for surfaces, the situation is much more interesting. It turns out that one needs to do a more complicated construction, not only involving the degree and the rank, or maybe the zeros and first term character, you also need to involve the second term character. And the construction that we usually use is due to Arcaran-Bertrand and depends on the choice of two parameters. Some parameter beta, which is just a numerical class, and alpha, which is an ample class. And this gives you some piece of the stability manifold of your surface. And a natural question here is, well, can you give more stability conditions? Do we know everything for surfaces? And it turns out that we know very little about surfaces. We know this small region constructed by Arcaran-Bertrand. After that, it's no man's land. We have no idea what's happening over there. And so maybe one way to start approaching this question is, what is at the boundary of this region? Is this region like unbounded? There are no limit points in this stability manifold? Or is there something else that we can try to approach? Today, we'll focus on the case when instead of having an ample class, we degenerate to a big and F class. So this is the pullback of an ample class via a birational map. And it turns out that people have tried this in many directions, in many situations. For example, Bridgeland himself sort of solved this question for K3 surfaces. So that in that case admits ADE singularities, possibly many of them. And then there are some results essentially contracting with one singular point, maybe just the blow up of a smooth point, or maybe the contraction of a minus n curve or an ADHN. And I was really interested into this question for a reason that will come out a bit later. And it turns out that one can construct many more examples. The statement's a bit technical, but what you have to keep in mind is the following. In that, instead of allowing the surface T to just have a single singularity of say a 1n, 1, singularity or something like that, here I'm allowing to have, first of all, multiple singularities at the same time. And also this includes cases where the singularities are cyclic quotient singularities, but with multiple irreducible components. Not all of them, sadly, but infinitely many of them. For instance, if the coefficients are all at least 3, that's completely fine. And so, as I was telling you, one of the key striking features of this result is the fact that you can allow, you get new singularities, which weren't present before, possibly many at the same time. And the way I was interested in this question was sort of opposite of what we hear, which is, can we allow other types of singularities? The examples that we had before were just ADE singularities or cyclic quotient singularities. So for me, I was originally interested in trying to see if one can get, for instance, elliptic singularities or something more complicated. it turns out that one can't, and one can show that the only curves that you can, if you have a smooth component in the exceptional locus, it has to be a rational component. So this immediately discards all simple elliptic singularities, or for instance, the contraction of a higher genus curve. It is unclear right now which type of singularities one can actually get. It's really interesting, at least for me, because you have this gap of, you are discarding smooth components of positive genus, and we know some ADE singularities, we know some cyclic quotient singularities, so the correct guess of which type of singularities can one get, there's a lot to be done here. The reason why I was interested in this question in the first place has to do with moduli spaces. One of the striking features of stability conditions, at least for me, is the fact that given a stability condition, you get a notion of a moduli space of semi-stable objects. One should think of this as analog of what happens in the case of curves or surfaces or higher dimensional varieties, where the notion of Giesecke stability or Mumford stability gives you a well-behaved moduli space. Same happens with bridge and stability conditions. Under mild assumptions, you get a well-behaved moduli stack that admits a proper good moduli space. And so the basic question that one could try to work with is, how can we understand these spaces? For example, if I fix a numerical class, is this moduli space empty? How many reducible components does it have? What is the local structure of this moduli space? Are they singular? And there are multiple examples studied, not only for curves, which is probably the easiest case, but higher dimensional varieties for sure. And the starting point of this tale is what happens with the constructions, stability conditions constructed by Arcand and Bertrand, for which it turns out that the moduli space that you get with the numerical class of a point is what you expect. You can recover the original surface S. This is what we call a geometric stability condition, and so the moduli spaces for these stability conditions are very nice, at least the ones that have numerical class of a point. So using the previous result that I told you, the first one about these limit points on the stability manifold, one can use this to describe new examples of wall crossing for surfaces. What I mean by this is the following: given a numerical class, as you vary the stability condition in the stability manifold, there is this so-called wall chamber decomposition. So the stability manifold gets cut out in pieces called chambers, in which it doesn't matter which stability condition you pick, the moduli space will look the same. And after you cross a wall, the moduli space may change and will look slightly different. You're parameterizing different objects. And understanding how exactly it changes is a really interesting question. This is, for example, what Bayer-McCree did in their paper about moduli spaces over K3 surfaces. And for me, the reason why I'm interested in this question has to do with one of these all stability conditions by Tramel and Chia, which they give a wall crossing phenomena that it's really weird. They start with from a surface and they get an extra component of different dimension, which is a behavior that doesn't happen for K3 surfaces. And so let me tell you how one can use the stability conditions that I constructed to get this phenomena. So basically you pick your favorite surface S admitting a contraction, say, of a minus n curve or something like that, and you construct a stability condition. Once you have your stability condition, you can use the fact that the stability manifold is a manifold to deform it locally. And that will give you a small region in which you have a bunch of stability conditions, and locally, you can describe explicitly how the walls look like. This is just a numerical computation. One of the chambers that is touching this, contains this point in its closure, is the geometric chamber. This is essentially by construction. We constructed this limit point as limit of geometric stability conditions. So we have one part in which we completely understand the moduli space. So to go to any other chamber, we wall cross each wall carefully and try to understand how the moduli space is changing. So to tell you a bit about what happens here, let me start with an example that sort of connect this old idea of Tramel and Chia with multiple curves at the same time. So let me start assuming that you have a surface S that has two disjoint negative rational curves, smooth that we are contracting them to cyclic quotient singularities. So the result that I told you at the beginning tells you that there is a stability condition depending on the pullback of the ample class on T. Using Bridgeland deformation theorem, one can deform this stability condition so that the central charge varies just a little. And the way that we will do this, I'm going to change the central charge so that now instead of having the pullback of the ample class, I'm allowing to add a small amount of either the curve C1 or the curve C2, the two curves that are being contracted by the map F. And the reason for doing this is that if epsilon1, epsilon2 are small and negative, this is now an ample class. So you recover these Arcara-Bertrand stability conditions. So the bottom left corner that you get correspond to the geometric chamber, and the moduli space that appears there is just the moduli space S, which I painted in blue. The two regions in red are due to Tramel and Chia, and these are these interesting phenomena that I was telling you. The moduli space that you get after wall crossing has this two-dimensional component, S, this N2 minus one-dimensional component, where N2 is the dimensional, sorry, minus the self-intersection of the curve C2. So you have a priori two components of different dimension, glued as follows. The curve C1 that is containing S is glued as a rational normal curve in this Pn1 minus 1. And the whole point now is, now that we have this stability condition in the middle, you are allowed to wall cross not only to the bottom right and the top left, but you can also wall cross to the other side. In which case, it's not too surprising one gets the surface S with these two components. And I say that it's not surprising because essentially what we're modifying is something related to C1 and C2, and these curves we're assuming that they are disjoint. It turns out that at the walls, and this is something that Tramel and Chia didn't do, one also recovers the partial contractions of the surface S contracting maybe one of the two curves, contracting C1 or contracting C2, and I didn't put it here in the picture, but at the middle you also recover T, the contraction of both curves simultaneously. And they sort of, they have this result in terms of objects, like they show that the space has to be in bijection with T1 or T2 or T, but the big issue that happens is trying to understand the local structure of this moduli space. One of the key technical issues that happens when you try to control the wall crossing is understanding how the local structure of this moduli spaces behaves. In the classical case of K3 surfaces, this is pretty much well understood due to the fact that we have a holomorphic form that help us a lot understanding the deformation theory. And so the local structure of a moduli space is controlled by the deformation theory of an object, the object that it parameterizes. In the good cases that we're parameterizing only stable objects, this is just the object that we have. If we're parameterizing more complicated objects, possibly strictly semi-stable, one needs to go to the polystable object. Basically, write it as sum of its semi-stable pieces. In that case, it turns out that the local structure of the moduli space is controlled by the uh, differential graded Lie algebra given by the derived ohm. So this is the ohm from E to E, and we just keep track of the Lie bracket obtained by composition. More precisely, the completion of the local ring of the moduli space at the point P is given by something completely determined by this derived ohm. So the whole point here is we need to understand this bottom right part, for which one would like to have a representative for this differential graded Lie algebra. It turns out that there are many ways in which one can try to do this, for example, by resolving by injective objects or by using Dolbeault solutions in the complex setting. In this case, for me it was easier to just use a check cover, compute everything in a model, and then glue everything together. This is something called a semi-simplicial differential graded Lie algebra. It's a mess, but it turns out to be doable. And so let me finish you by telling you what happens when you have two curves intersecting at a point. And I think this is the first behavior that for me was a bit unexpected. So now I'm assuming that the surface S contracts uh, two curves to a cyclic quotient singularity. So now the bottom left part again is this the geometric chamber. You have to think of this as sort of looking at the ample cone around this point. And the red parts are these two moduli spaces constructed by Trammell and Chia. But there are now three other regions that one can look at. So for example, what happened for the region M that I put in green on the right? The answer is even more complicated than the previous ones. I wrote a precise description on the top, but let me tell you what happens with the picture on the bottom, where I'm assuming that I'm constructing 2 minus 3 curves to a point. In that case, you have three different components. The original surface S, you get the blow up of P2 at a point, and you get a copy of P3. So this P3, you take a line over it, and you take a conic passing through one of the points of the line. So like in a complementary P2, you glue the conic to the surface S using one of the two rational curves. You glue the line to the exceptional divisor of the blow up. And the curve that I put in blue in the blow up is the pre-image of a conic in P2, so that the conic passes through the point that we blew up. We glue everything together, and this gives us the description of the moduli space. So in the example that I just told you, it has two components of dimension 2 and one component of dimension 3. It turns out that the dimensions are written over there. It has a two-dimensional component, and one minus one-dimensional component, and one plus and two minus three-dimensional component. And I think that's everything that I had to tell you today. Thank you so much.
Thanks so much. Any questions? So, sorry, I have a question. So you mentioned that you thought about this, trying somehow to understand exactly what are the singularities that can show up. So do you have any results in this direction? So,
Well, not beside what I told you. So um, this theorem tells you that the singularity shouldn't have smooth curves of positive genus. So that discards a lot of the possible singularities. And uh, I also contributed proving a bunch of cyclic quotient singularities. My guess is that one should expect that that the singularities that can appear are exactly rational singularities. And this has to do with the fact that when you have a rational singularity, a surface T with only rational singularity, the derived category of T can be realized as a Verdier quotient of the derived category of S. But I think we're a bit too far from that from now.
I see. I see. Thanks.
Mhm.
And also, I'm curious, so when you take this limit and get a pullback class from the surface T, And how does this moduli space on S and the moduli space on T compare?
That's a, that's a good question. So, well, first of all, one needs to be a bit careful here because the moduli space, of course, depends on the choice of a numerical class. And these stability conditions live only on S, so a priori it's not immediately obvious that one actually gets a stability condition on T. Of course, one can like sort of copy beta and Eta and try to mimic the construction on the singular surface T. This is due to Langer. I think in general one should expect that the push forward maps semi-stable objects in S or semi-stable objects on T. I think to Yang Chu, which is one of the authors of the results that I told you before, has some partial results on this in the case of a single AD singularity, but in general it's very unclear what's happening.
Okay, yeah, thank you.
Other questions or comments? Okay, if not, thanks again for a very nice talk.